The headline says the Trump administration has abandoned its fight against wind energy bans. The other side of that coin, however, is that they stopped fighting because there was simply nothing left to stop. This isn't a policy victory achieved through legislative maneuvering or political compromise. It is an engineering inevitability born from hardware maturity. For years, critics argued that wind power could never scale without massive subsidies and constant political protectionism. They were wrong about the why of this boom, but right about the result being inevitable once physics caught up with ambition. The industry did not wait for permission or tax credits to surge. It waited for the turbines themselves to become too efficient and reliable to ignore. We are witnessing a moment where hardware density finally outpaced intermittency fears, making the ban on wind energy obsolete not because laws changed, but because the physical machines have fundamentally improved their output per square meter of land. To understand why this shift happened, we must first look at the old problem that defined the debate for decades: the intermittency wall and the nightmare of maintenance failures. For a long time, opponents argued that wind power was too unreliable to be part of a modern grid. They pointed to small rotors on older turbines that struggled to capture enough kinetic energy from low winds, resulting in erratic output that required backup fossil fuels to stabilize the system. Furthermore, these early machines suffered from frequent blade fatigue and failure during storms. The argument was simple: if you need constant repairs every few months and cannot guarantee power when the wind drops slightly, you have a liability, not an asset. This maintenance downtime became the primary weapon used by regulators who imposed strict bans on new installations in communities concerned about noise, sightlines, and grid stability. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The engineering pivot began with solving the density problem through massive rotor scaling. The historical constraint was that to get more power from wind, you needed larger farms or better locations, which meant expanding transmission corridors and facing more local opposition. Recent manufacturing breakthroughs changed this equation by maximizing kinetic energy capture within a fixed footprint. Modern utility-scale turbines now utilize significantly larger rotor diameters than their predecessors. When you double the diameter of a rotor, you do not just get twice as much power, you exponentially increase the swept area, allowing the machine to harvest wind speed and volume from a vastly greater column of air above it. This scaling allows them to capture more energy per square meter of land, effectively increasing capacity factors without expanding the physical farm size or requiring new transmission lines for every megawatt added. The result is that communities can now see higher value in their leased land with less intrusion, as fewer turbines are needed to generate the same amount of electricity compared to a decade ago. While rotor scaling solved the density issue, the industry also had to conquer the reliability gap through a revolution in composite blade materials. Historically, wind farms suffered from high maintenance downtime because traditional fiberglass reinforced polymers were prone to cracking and erosion under variable weather conditions. This was the key argument used by opponents to claim that grid instability would make wind energy too risky for widespread adoption. The industry has now deployed advanced composites that are lighter yet significantly more durable than their predecessors. These new blades can flex with high winds without snapping, absorbing stress in ways older materials could not. This material science shift means farms can operate through extreme weather events with drastically reduced frequency of repairs and failures. By ensuring higher operational uptime even during volatile conditions, these advanced turbines now provide consistent baseload, adjacent power without relying on intermittency as a permanent liability. The political landscape is reacting to this physical reality rather than driving it. While Energy Secretary Chris Wright confirmed in February 2025 after his nomination in November of the previous year, argues for ending perpetual subsidies based on market maturity, the data shows these cuts are simply acknowledging that the industry no longer needs them to survive. The levelized cost of energy has dropped so low due to manufacturing efficiency that federal tax credits from acts like the Inflation Reduction Act have become secondary to pure competitiveness. Consequently, local regulators who previously resisted new projects often lag behind this physical reality. Communities that once cited noise concerns or setback distances, sometimes as specific as 200 meters from areas of concern using ratios of 1.1 times the turbine height, are now seeing value in land leases and lower electricity costs because the technology has become less intrusive and more productive. Nighttime sound thresholds, which were previously a major sticking point for residents trying to sleep, are no longer an issue with modern designs that have pushed noise levels well below typical daytime limits. This shift signals a fundamental change in how we build infrastructure. Hardware is now the driver of energy transitions, not just legislative battles. Future debates will be won or lost on manufacturing capabilities regarding how big we can make blades and what materials last longer, rather than purely on political outcomes. The perception that wind power was too unreliable for a modern grid was accurate in 2005, but is no longer physically true due to these density and durability breakthroughs. Wind energy now generates over 10% of the United States' net total energy output, driven by engineering efficiency rather than government handouts. This makes the technology resilient against future political shifts. You cannot ban what is already cheaper and more reliable than the alternative, regardless of who sits in the White House or which party controls Congress. The abandonment of bans was just a lagging reaction to hardware maturity, because once physics delivers on its promise, policy simply has no choice but to follow suit. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.